Um, Hello everyone, and thank you for attending the AARC research seminar. I am BC Min, Director of the AARC. It is my great pleasure to introduce our speaker today, Dr. Qiben Yan. Dr. Yan is an associate professor of computer science and engineering at Michigan State University. His research focuses on cyber-physical systems, security, trustworthy AI systems, wireless communication, and blockchain security. His recent research identifies security vulnerabilities in autonomous driving and voice AI systems. He received the NSF CRII Award in 2016, Best Paper Award at IEEE Second and ACM Census in 2021, and a Best Paper Honorable Mention at ACM CCS in 2022. His work has been featured in BBC Radio, Scientific American, and Forbes. His recent research has been supported by NSF, DOE, and Ford. He received his PhD from Virginia Tech. Without further ado, please join me in welcoming Dr. Yan.
Thank you. Thank you, everyone. Thank you, BC, for the warm introduction and your hospitality. This is my first time at Purdue University. I'm really amazed by the beautiful campus. So I'm so glad to be here to talk to you about my recent research on this trustworthy AI models topic. And this is a topic that my group has been investigating since the last 2 years. So we have some research results that I want to share with you. So the talk is about building trustworthy AI models for autonomous cyber-physical systems. By trustworthy AI models, I really want to talk about the robust AI models against attacks and the security threats. And we want to look at that from a security perspective. How can we robustify those AI models? So let's get started. So this is the evolution of smart devices and systems. My research also follows this trajectory. So starting from 1990s, we have the first smartphone, the IBM Simon. And after that, in 2007, we have iPhone. The debut of iPhone really revolutionized the field, and we enter a mobile era. And after that, we have seen a number of IoT devices now start entering our smart home environment with smart speakers, wearable devices, smart locks, and even we have seen the development of self-driving vehicles. And nowadays, since 2022, we have a development of ChatGPT, and we have seen a plethora of cyber-physical systems that are developed using those language model or large models, including those voice assistants that using ChatGPT to interact with users, and also the embodied AI aspect that have been really blossoming under this development of AI models. So with the growing diversity and the complexity, we have really seen there are more risks, cyber risks and physical risks from adversaries. And I really want to look into this trend. First, I started looking at the mobile security and look at the IoT security. Nowadays, I'm more focused on the cyber-physical systems and AI model security. So let's take a smart home as an example to illustrate what are the cyber-physical system security problems here. So in a typical smart home, we have different types of sensors and smart speakers that can interact with users. And the attackers can reside beside the home, outside inside the room that may compromise devices. And also the attacker can launch attack remotely through the internet. So we are trying to explore different components of the system to see whether they are vulnerable against security attacks. From the wireless perspective, from the networking systems and AI models and sensors and applications, all those components are under threats, under cyber threats. And our goal really try to address those cyber threats before the attackers are exploring that. And let's zoom out to a smart city scenario. Now we have autonomous vehicles that are driving around. We have robots that are cleaning up things in our homes. So we are still looking at those different components from the application to the wireless spectrum to see how robust they are against security threats. By the way, those images are generated by ChatGPT. So we have seen a tremendous societal impacts of the security incidents. For example, we have seen smart home devices being compromised to launch denial of service attack. We have seen EV charger being compromised, and Tesla have this phantom braking problem. In fact, when I drive from East Lansing to this beautiful campus, I use the FSD to drive for me. I experienced at least 3 times of phantom braking during my trip. Right? So there's nothing around, but it just breaks. I don't know what happens, but this is a quite common problem. I think if anyone is driving Tesla, you probably have experience of this phantom braking. And this could cause some dangerous situations. And in my research, I really want to understand why that happens and how can we fix these problems, right? It's not only the problem of Tesla, there's other autonomous vehicles that facing similar problems. So in order to understand IoT and CPS threats, I tried to look at that from 4 different perspectives. First of all, the threat vectors now they are becoming more sophisticated and better organized and harder to detect. And they are sometimes they are using AI to power their attack. And I look at from the system perspective, there are system and model vulnerabilities that attackers try to exploit. And there are malicious code and the botnet. And denial of service attack is causing problems to the networks of those systems. And nowadays, we are more focused on this adversary who have high capacity. They know how the defense works, and they try to bypass those defense to reach the core of the system. And we call them adaptive adversaries. And in our research, we really want to look at the model security and adaptive adversary, how secure, how robust our system are against those attackers. So in order to build a good cyber-physical systems, we want to think about defense mechanisms that can provide security, privacy, reliability, and robustness to our systems, right? And there are some subtle differences between reliability and robustness. Reliability means that I want the system to function expectedly, like to drive the expected outcome, while the robustness means that I want the system to function even under adversarial attacks, right? So our defense mechanism really want to provide those 4 features, right, in order to provide really reliable and secure cyber-physical systems. So to understand these cyber-physical systems, I took the autonomous driving as an example. So today, my main focus would be on the autonomous driving systems. And I want to illustrate how robust is the perception of the autonomous vehicles that's connected with the phantom braking problem that I was experiencing when I came here. And the second one that I want to talk about is how secure is the end-to-end AI models of autonomous vehicles. Right? End-to-end models include the perception and the control of the autonomous driving. So first, let's look at the perception, security of the perception systems. And to understand the perception, I learned from the vision science. So you know that in human vision system, we have this so-called visual pathways. And visual pathways are those neural pathways in your brain that can take visual inputs from your eyes, those are sensors, and send them to brain, right? And brain will process those sensor input to make sense of what we are seeing. And there are really, so the neuroscientists or the vision scientists really tells us there are several stages of perception that is happening in your brain. There are 3 levels that I explained. The low-level perception is happening in the V1 region of our brain, and V1 is cortical region of our brain that is very close to the eyes. That region is trying to detect the edges and contours of a scene and an object. And there's a mid-level perception that are dealt with V2 to V5 regions on our brain that are trying to sense the shape, the motion, and the depths of the scene. And there are high-level perception that are dealt with using inferior temporal gyrus. This is a component like here in our brain that is close to the back head. And this part is trying to deal with object recognition, like what object it is, and try to make semantic understanding of the scenes. That's actually how we see the environment. And the vision expert, the computer vision expert, are learning from the neuroscientist to develop different algorithms for edge detection, for shape detection, depth estimation, right? But they are really start from the edge detection. If you search for the most famous computer vision paper, that paper is trying to design an algorithm to detect the edges, right? So we are also like starting from the low level, mid level, high level. And this connects us with the autonomous driving systems. This is what I illustrate that going on in our field from low-level perception to mid-level to high-level perception of these autonomous driving systems. So first, we use sensors just like our eyes, but it's an enhanced vision system, right? Not only eyes, but we have radar and LiDAR to take images in, and we do the low-level perception to sense the data and provide some raw sensing input. And at mid-level perception, we are doing the motion sensing, object detection, depth estimation. Those are the mid-level perception tasks that we are also dealing with in our human brain. And finally is high-level perception, including object detection, object recognition, motion-related stuff, and also scene understanding. These are more of high-level tasks. And in my research, I want to look at the whole spectrum of the models that are developed under computer vision domain. And I want to evaluate how robust they are under attacks. Specifically, today I want to focus on the depth estimation algorithm and object detection algorithm of the computer vision. And I want to illustrate that they are not so reliable. They are actually not so robust against adversarial attacks. And in future, like in my future research, I will more focus on the high-level perception tasks. So this is really what guided my research, and we are trying to ask two questions to these autonomous driving systems. The first question is, what are the physical attacks that can compromise perception tasks, including the object detection, object tracking, and depth estimation? And second problem is more on the defender perspective. How can we design effective defense to achieve more resilient perceptions, right? So we all know that we have two different types of autonomous systems that are very popular, autonomous vehicle and drones, right? Although they are very different systems, but in terms of the sensor suite, they are pretty similar. So they use LiDAR, camera, radar, acoustics, although like the drone doesn't use LiDAR much because LiDAR have a big form factor and it's very expensive. But mostly they share the same type of sensors. So the perception problems that if we understand the perception vulnerability of one system, that can be really applied to attacking another system. So let's look at a camera as an example. So camera is basically the most important sensors that are used in autonomous driving systems. And it's also very easy to study, and camera, you can buy a ton of it and study each vulnerabilities of different camera systems. So we started from cameras and expanding to radar and LiDAR like in the later research. For the cameras, we have seen some existing attacks that try to compromise the cameras from the physical world attack perspective. So you are launching attack from the physical world to attack the cameras to cause some perception errors. So this is the very first attack that tried to use a laser pen to point it to the camera and to cause some problems with the camera vision. Right? And what it does is really to damage the CMOS sensors in the camera. Right? Because of this damage, and the camera will not be functional after this attack. And we have also seen such attack that try to create a ghost image. For example, by using a projector to project a stop sign onto the camera, right? To let the camera recognize a stop sign, a fake stop sign, right? But it's actually not there. And we have also seen the attackers try to launch this phantom attack to project a fake human being on the road, such that the Tesla vehicles can recognize this fake person. Right? And you have seen there's different type of camera attacks. And in our research, I try to understand how vulnerable those camera systems are and the algorithms of this camera system are against those type of physical artifacts. And the artifact that my research try to exploit is from the optical imaging research. In optical image, when you try to send a strong light to a camera, for example, here I use the flashlight of an iPhone to directly shoot into my camera. My camera not only see the light, my camera also have artifacts. Right? One artifact is this strong glare. The other artifacts are the ops that are generated. Right? And you can actually move around this, the location of the phones to generate the ops and the glares at different locations. Right? Even you move very far away, you can see there's still a ops here, and there's a strong glare here. Right? And this is not a problem for a single camera. This is a problem for all types of cameras. If you use, for example, your camera to shoot a video of a rising sun or a sunset, you would see those ops and glares as well. And this is called lens flare effect. And it's caused by our non-ideal lens systems of our cameras. And it can generate several undesirable artifacts, right? This glare and ops. Right? The problem is really we have multiple lenses in our cameras, right? So when you are shooting a light into the camera lens, it not only generates the image of the light source, but it's also being reflected multiple times through multiple passes to generate ops, right? And these ops actually can be taken by the camera systems, right, to create a fake object, fake obstacle, right? So that's really what my research try to understand, whether we can utilize these artifacts. And this generation of glare and ops is happening for different types of cameras. And you can see that the glare and ops, they are central symmetric, right, to this image. Like it's central to this diagonals, right? And every camera systems would have this glare and ops being generated. And now we are going to find a target of our threat. So this threat is using these ops to create a fake obstacle to our cameras. Right, our target is this depth estimation algorithms using stereo cameras. So this is a typical stereo cameras, ZED camera that was used for gaming and sometimes used for robotic vehicles and used for autonomous vehicles as well. Right? And they have two cameras, right? And it's just like human eyes. They use these two cameras to look at the object and to figure out the depth of the object, right? So they use triangulation to figure out the depth, to see how far away this object is. And in this camera, they are taking two pictures, right? One is left image, one is right image, and try to combine and do a depth estimation. Right? So as I said, this has been used in drones and robotics and autonomous vehicles. And our research called the double star is try to basically project a light into these two cameras to create a fake obstacle, right? To create a fake obstacle. And the attack factor is using a projector or a light sources, right? Not like laser, but a flashlight to project into this camera, right? And you can create a fake obstacle. And we develop this projecting attack with two different light sources. It can be a flashlight, right? It goes into the camera of flying drone or autonomous vehicles, right, to create a fake obstacle. And the challenge is really how can we control the shape of the obstacle? How can we control the distance of the fake obstacle from my camera? Right? And in order to control the obstacle distance, we develop two types of attack called the beams attack and the ops attack, and the three types of attack patterns called X-shape attack, trapezoid shape attack, and the triangle shape attack. Right? So let's look at the trapezoid shape attack first. Trapezoid shape attack is really easy. So we have two flashlights, like the left flashlight project to the left camera, the right flashlight project to the right camera. And in this way, you can create two images. And because of the vulnerability of the camera systems and also the depth estimation algorithms, it's try to take the center of the image, right, and try to match them together to see whether there's an object. Because we have ops like near the center and on left image and right image, and this ops will be detected as one single object, right? Although there's no object there, but actually you will detect these two ops as a fake object. So you can see if we look at the depth map, you can see that there's a fake depth appearing here. And this is actually very useful to create a far distance object. Right? You can create an object that is, for example, 10 meters away, although there's nothing there, but it's create this kind of object. Right? And I suspect that this actually is one reason of the phantom braking, but we try to prove that right now. For example, if you are driving under the sunset scenario, you will see this kind of ops on your camera, and it might detect a fake obstacle and try to and the car will brake. Right? So this is called trapezoid attack, and this X-shape attack is a different pattern. So my left projector projects to the right camera, and my right projector projects to the left camera. And in this case, instead of the glares, I will actually match the I will match the glares as a one single object. And you can see that the glares are much stronger lights. Those are much stronger lights. And this will have an effect of creating a near distance object. So this object is much closer to my camera. Right? And you can see on the depth map, you can also see that there's a fake obstacle appearing here. Although my projector are like rather far away, but in a near distance, you can see there's a fake obstacle. And this X-shape attack can create a fake obstacle that is nearby of the vehicle. And we can even try to create two different objects. So when we have P and Q that are covering like both cameras at the same time, in this case, you are actually creating two objects instead of one object. Right? In order to launch attack, we can have two flashlights, like you can move around and to really target the drones, right, to create these obstacles. So here we have an experimental setup. So here I use two projectors, but it can also be a flashlight. And we use two Canon lenses to basically focus the lights onto the camera of the drone. And here is a DJI drone is our target. It's using a stereo camera, using two cameras to sense the depth of the image. And this is so this can also be done to those different types of 3D cameras, and we also use them as a target. And my students, he did this research under very cold winter, so she has to be outside and shooting this. And actually, her neighbors always complain about it because he saw a lot of strong lights happening. But anyway, we got a large table of results, and this is the attack distance from 1 meter away between the camera and the light to 50 meters away. We can create fake depths, fake object at a certain distance for different types of attacks. You can see in the daytime, we can reach attack distance of from 8 meters away. We can create fake depths, like we can control the angle to create fake depths from 1 meter to 40 meters away. And it actually very good at night scenario. Even with 15 meters distance away, we can create a fake obstacle that is 60 meters away. So you can see that maximum we can create 15 meters fake depths at night and 8 meters fake depths at the daytime. Right? The impact of this type of research is really to understand the phantom breaking problems and to see whether attackers can use this kind of a simple physical attack to create a fake obstacle, and that can be understood by the depth estimation algorithms, and to create this like fake vision, right, of these systems. And we try to understand why this happens, right? And the real problem is from the both from the camera side and also from the AI model side. In the AI models, they tended to use like low-order perceptions. By low-order perception means the algorithm itself doesn't really understand the scenes, right? So they just try to take the pixels and to match the pixels from 2 images into the single image. For example, we try to add a patch on the left image and on the right image, right? Even with this single patch, right? And the depth image will create a fake depth on this image, right? And because the stereo camera tried to understand like there's a similar features in these 2 images, then there must be an object there, right? It doesn't try to really correlate these 2 images to understand what is really there, right? So there's no higher order perception. I think this could probably be solved by large language model when you have a better reasoning of this scenario. You could detect this is fake, right? But at current AI models, you really cannot differentiate like whether this is fake or real. So we have done an experiment in a very cold winter. Right? That's the coldest time in the year. My students, she wear a lot and try to project the 2 lights onto the camera. Right? We can look at this video here. Yeah. So here,
the home point has been updated.
So here is a DJI drone. When there's no attack, you can see that it detects the depths at 5 meters away. But when we launch the tag, the depths become 0.45 meters away, right? So basically, instead of detecting the real object, that is my student, that is 6 meters away, it actually detects something here, like only 0.5 meters away, right? Because of these 2 light sources. Because of that, the drone will not move forward because it detects object in front of it, so it stops. It causes sudden break. It can also shake the drones by changing like the location of the obstacle. The drone try to avoid the obstacle, then it will shake. It might also cause a fall off the drones. It could also drift away the drones, right? So when the drone is moving, like try to move ahead, when came across the obstacle, then it will drift away, right? So it will getting away. We figured that this could be a good approach to like actually protect us from drone surveillance. So when you have seen a drone coming by, you can use these light sources just to drift it away, right? So this is another side effect of our attack, right? So this is about the perception problems under these projection attacks. Right? I want to move a little bit further to the object detectors that we are targeting. You probably have heard about, question? Oh, sorry. Yeah. So you probably have heard about these stickers, right? So you can put these stickers on the stop sign, right? And then the stop sign will be changed into a speed limit, right? And this is a very famous paper that was published in CVPR, right? To change the signs. And this is another paper. This paper is actually from Purdue Purdue University, Professor Stanley Chen. He developed this called the optical adversarial attack. They project lights onto a stop sign, then the stop sign will be recognized as a speed limit, right? So instead of using stickers, now it's more advanced. It can be using projectors to project images on the stop sign or some objects, right? And this is actually what the object detector does. Object detector tries to find this bounding box of the object, and then to detect whether this is a person, this is a handbag, this is a cars, right? Try to detect those kind of things. And in the object detectors, like in the projection attack, we can project the image onto the stop sign, right? And to make the stop sign being recognized as a different sign, right? But current projecting research just stopped at this stage, right? So they wouldn't go beyond a stop sign or sign recognition. That motivates us, like, really to push the envelope further, right? To make the projection attack even more powerful. So that's how our research is, like, because we think that most objects have curved 3D surface, right? So it's not a plane just like a stop sign. You have vehicles, you have persons, right? And we want to think about how can we project light, like, onto a vehicle that to change the object detector results, right? And this is my collaborator. Like, he worked in IBM before, so he used this adversarial patch to be put on the T-shirt that can make the person disappear from the surveillance cameras. So you can see when you wear this adversarial patch, the person just disappear from the object detector, right? And I collaborated with them. I try to think about, like, whether we can use this kind of technology and convert it to a projection attack. So this is how we come up with this 3D projection attack. We try to consider there's a surface distortion, there's angle distortion, right? And we want to see if the object detector will misrecognize those objects. Our goal is to design a transient and physical realizable projection just by projecting those patch, right, onto the 3D object. But there are several challenges here. The first is, how can we map the project image, right, onto the object surface, right, with the same color scheme, right? So for example, when we project a pure blue light, right, onto a person's T-shirt, you can see that the blue light becomes much lighter, right? Much lighter. It's not the same as the data source that I gave to the projector. Right? So we have to develop a color mapping model from this projected light back to the original source, right? To see what kind of a color I need to project into the object. And the second challenge is, how can we transform the patch onto the 3D surface to ensure its effectiveness? So here it's a 3D surface, right? And the vehicle can actually shift angles, right? And we need to consider this 3D structure to consider whether we can use geometric transformation to design this patch, right, to be projected on this vehicle, and it will still be effective to attack those object detectors. And the third challenge is how to ensure the attack in a dynamic environment. So for example, the vehicle can change angles, right? So how can we make the patch still work under different angles, right? And we can achieve that by enhance the training set, right, using different transformations and augment data using viewing angles, the different distances, different brightness, and different blurriness. Basically, we are kind of try to do a much larger training in order to find this optimal patch that can work under different environment, right? And this is what we end up doing. Right? So we developed this 3D projection attack pipeline. First, so we want to develop this color projection models, right, to find the projected object of this benign object. And then we want to develop a geometric transformation model that try to transform the object, the projected object back to our original image, right? So this is the 3D patch, and this is the original patch. And by doing this optimization, we will be able to, our goal is really to optimize the patch that we can project, right, to the vehicle and can make the vehicle disappear or change it into another object, right? And we have so we have a loss function that try to reduce the detection score of the object, maximize the detection score to a target object, and we also try to reduce the variation, right, the changes of the image itself, and we also want to make sure that the color projection is very accurate. So this is p-norm of the projected image with the original object image. Try to make sure that this image are as close as possible, right? So let's go a little bit into the details about the color mapping model. We try to formulate a color mapping by using this equation. So we have a 3D object surface, we have a projected image, and we have a color overlay that was really appearing on the object, right? So our goal is to really minimize the difference between the projected image and our expected image, right? So O is our expected image. This is the projected image, right? And by minimize this difference, we can really find a good color mapping model, right? And this color mapping model is using a deep neural network itself. So it's also a deep neural network. It's being optimized using this loss function to find it out, like what is the best transformation, the color transformation from my original image to the projected image. And for the geometric transformation, we do a very similar thing that it's a technology called a thin plate span TPS transformation. This is try to deal with this image wrapping and deformation of the image in a 3D structure. And in this transformation, we have a linear component that try to map the image like linearly to the projected image. And also there's a nonlinear component because the deformation is nonlinear from my original image to the 3D image, right? So by considering both linear and nonlinear, we will be able to create this model like to really figure out a good transformation, a good 3D transformation, right? And TPS is an existing open source platform that we can use actually to maximize our accuracy of the projection. And going into this attack scenario, so we have a victim camera, we have a projector, we have a vehicle that is a robot car, right? It's 1/10 of the real car, right? Then our target attack detector, object detector are the YOLO and the mask RCN, and we use the object misdetection rate to evaluate the results, right? So here you can see after, so this is our original projected image. This is after the geometric transformation. And when we apply that to a real vehicle, this is what the camera really gets, right? So this is really captured by the camera. And we designed the patch. So this is the patch that we designed to be projected on the vehicles, right? So you can see this is a real image, but after we project it on the car, it becomes a little bit different, right? And this is actually the patch that we want to optimize, right? So this is the real patch that we applied to the vehicles. And this is a visualization problem for Vero and RCN. You can actually see that after we apply this attack, the sensors so it can really detect the object. So this is a misdetection rate, right? So when we have no attack, the misdetection is really low. But after we launch the attack, right, so you can see a spike of the misdetection rate, right? Although there's also a misdetection rate under the strong light conditions, I think that's because of the impact of the ambient light. Okay. And we think about like this attack is really happening, and this ambient light have a huge impact, right? And there's also a moving target. How can we deal with the moving target, right? And there's also a potential defense that we need to develop, like using adversarial training and try to verify the consistency of detection over time, whether we can really effectively detect such attacks, right? So let's look at this example demo that we try to project an image, right? So this is without attack. So you can see that we can very accurately detect this object, right? It's a car, and the percentage is very high. So when we launch the attack, so here is, this is still the, so when we launch the attack, you can see, like from different angles, right? From different angles, we cannot really detect these vehicles, right? So even like we shifted to another direction, so for some split seconds you can detect it, but after a while it disappears. It disappears from the object detector, right? So this is really what happens when you have this adversarial patch well trained, right, to be projected on the vehicle, and it can be really robust against the different deformations, different types of transformations. Right? Any question about it? Yeah. Great. Yeah.
So the adversarial patch is also generated using a machine learning model, is that right?
So yeah. So the adversarial patch is basically we have optimization. It's optimization problem, right? Optimization problem. So you have to know it's a white box attack. So you have to know the model that you are attacking, right? And based on the model, so you try to find the best patch, right? Using a loss function, right? Always you try to like find the best patch that would work, right? For different types of models, yeah. So it's a target model that we are attacking, and based on different models, you can craft different patches. All right, yeah. So my final topic that I want to illustrate is another very simple attack using optical lens. In the literature, like there's a lot of researchers try to attack this depth estimation algorithms for the monocular camera. That means you are using cameras to identify the depths using one single camera. Right? And there's some attacks that try to add perturbations, right, to these vehicles, right, such that somehow I can actually remove the vehicles from the depth image. However, this attack wouldn't work in the physical environment. And we can also add a patch, like add a patch here, right, to make the vehicle appear like closer or farther away. However, this kind of patch is easily detectable, so you can see like this patch, you can really, like everyone can see it, right? It's really detectable, and the patch is very scene sensitive. So for different scenes, it sometimes works, sometimes doesn't work, right? So we really want to come up with a universal backdoor, a black box attack that can be very robust against like optical, using just optical lenses. And our idea is really from this digital transformation, right? So here is a typical like image processing. So I want to change the depth of the vehicles, right? So then I apply a lens here, optical lens, then the vehicle appears farther away, right, instead of closer by. So this is when I reduce the size of the object, then you can see that the vehicle appears farther away. On the depth image, you can see that we can actually change the depth of the obstacles by changing the size of the object. So here comes the lens attack. Lens attack is just applying a lens like onto the cameras of the vehicles, right? So this is a Tesla car. I can attach a lens here. I can attach a lens here, right? Such that the camera will see a different depth image, right? And we try to understand like how this could really cause problems. And yeah, so we try to apply like the concave lens and the convex lens to make the object appears farther away or appears closer, right? Just to change the depth estimation result. And you can see that we are using this optical principle. This is like high school physics. You use optical lens, and you can change the object that was appearing right on the camera. And by changing the size, the distance between the lens and the camera, and also changing the focal length of the lens, so you can actually change the distance, right? You can change it farther away or closer by. So here we add a lens to a camera, right? To a camera, and then we can actually try to change the depth of this camera, right? So using this kind of a feedback loop, we will be able to find out like what is the best lens that we are going to use that actually can change the depths, right, to the target depths. And we can apply a lens like in addition to the camera lens. So this is a camera lens, and we can apply a concave lens or convex lens, right? It can actually change by changing the distance between these two lenses. And you can change the appearance of this object. So here we launch a tag to a real vehicle. So in this case, we are using a real vehicle, have a camera here, and we apply two different sets of convex and concave lenses, right? And to attack this car. So using in the digital world, you can obviously see that when we change the size of object, you can see on the depth map is also changing, right? So it's also changing from farther away to the closer by. This is from farther away to the closer by, right? So you can just change the depth to actually change the distance, to change the perceived distance. So we find out that the most impactful result comes out of enlarging the image. So when you have 3 times of enlarging, you can actually achieve 100% of difference. So this ADI is the attack distortion rate. You can change 100% of difference of the depths, of the real depths, right? So that can really have a huge impact like to the perceived image. And you can see the impact in the physical world when we apply the lens here, like it becomes farther and farther away. And when we use this concave lens, it becomes closer and closer, closer and closer. So let's look at this, this video here. This is for the concave lens attack. We use the focal length of 20 centimeters. So you can see this, this lens, when it applies to the camera, so the vehicles appears farther away, right? Much farther away. And this is consistent with the camera view and also consistent with the depth map. And on the right-hand side, yeah, so this is another focal lens. You can make it appear even farther using a different focal lens. And this 15 meters is even farther away, right? And let's look at this convex scenario. So convex scenario is the amplifying the image, and it's very effective. So when you apply this convex lenses, so you can see that the car becomes really close, right, at this time, and then the car will possibly brake. And when we change it to another focal length, yeah, so it's a different effect. And then when the focal length is 50 centimeters, so you can change a little bit of the size of the vehicle that, yeah, really changes the depth estimation result, right? Yeah. So this is what really guides my research. I try to understand what's happening with those camera systems and those AI models, right? To see whether we can improve or enhance the perception algorithms and also the camera sensor itself, right? So I first want to characterize the perception illusion, and we call this perception illusion. And then we want to do the sensing enhancement and data fusion. And finally, we want to use large language model or like reasoning engines to really understand the things to provide a better defense, right? So I guess the main takeaway here is that these cyber-physical systems are really vulnerable to this physics-inspired and model-aware attacks. It's not only digital attack, right? It's really happening, like really effective in the physical world. And the attacks can trigger AI models. It can sometimes also trigger, trick the human beings, right? Human drivers. And basically automated defense methods are really needed. And there's arm race between attacker and defenders, right? And in order to defend against those attacks, we need a signal level and a model level enhancement, right? To really make it work. Right? To expand it a little bit into the end-to-end AI model perspective. So the AI model in the autonomous vehicles not only dealing with the perception, right? Perception is just one part of it, right? And the bigger things are, we have perception, we have decision making, we have the planners, right? And they are all taking data from the environment to make a decision. And in the traditional vehicle scenario, these are different systems, right? So perception have a perception system, decision making have a system, planner have a system. But nowadays, like those full self-driving systems, they are trying to develop end-to-end AI models that could do different types of tasks, right? They could do perception, that could do decision making, that could also do the planning, right? So we are trying to understand, like, if these different modules can be attacked, and I would assume that these AI models, rather than being more secure, they are actually being more vulnerable, right? Because they are doing different tasks, right? If I launch attack to the perception, previously I can only compromise this component. But nowadays, I'm compromising like everything inside this pipeline, right? And that's what my current research is try to develop new attacks or understanding the security of these end-to-end AI models. And in order to defend against the attacks, those are several methods that we are investigating: sensor fusion, model pruning, certified robustness, formal verification, and pre-trained robust models, right? And those are different methods. I'm collaborating with AI researchers, right? Try to figure out what will be the best, really defending mechanisms for all types of security attacks, right? Towards these end-to-end AI models. So I want to leave you guys with this multi-layer view of this IoT and the cyber-physical system research. I started out as a sensing or device security researcher. I try to understand the device, right, and how secure they are. And then I expanded myself to understand the communication and networking perspective, right? And nowadays, I'm really more focused on the application and human-computer interaction and the model side of the paradigm, right? To understand how secure these cyber-physical applications are, right? Using this understanding of the AI models, right? And try to understand how vulnerable they are, right? From the physical attack perspective. So in order to study this trustworthiness of systems, I think our security researchers or AI researchers, we need to collaborate with each other to really understand what are the data that are useful for us, right? And to make sure that we have the whole attack spectrum under our investigation, right? We don't miss anything. And we need to really collaborate with AI, right? So we couldn't just do our own work. We have to work with AI researchers to find out this security research and even help us finding out good security problems, right? So with this, I want to end my talk and thank my students. This is really their contribution, their work. I really thankful to them, and some of them actually become a faculty in other universities. Right? Finally, I want to welcome everyone to visit MSU. We have a large campus just like Purdue, And we are very big like in the football. So this is a very big football stadium. I hope everyone come and visit us. Thank you.
Right. Thank you for the great presentation, Dr. Yan. Now we have time for a few questions. So now, since we are recording these seminars, if you have a question, please use the microphone. Maybe go first.
Yeah, thank you for the great presentation. This fascinating work. So I had a couple of questions. The first of which is, I know you talked about attacks on optical systems, like optics, using cameras, stuff like that. And so I was just wondering if some of these systems that try to perceive depth, do they use camera systems that operate on similar focal lengths? I have a device in my car. You might have heard about Comma.
Yes.
Right. So I have a Comma device, and it does a great job. I don't face any of those phantom braking problems, stuff like that. But I think so that the device uses two cameras. One is like a telephoto camera. The other one is like a wide-angle camera. So I don't know if you have similar experiences, or you can recreate the similar effects when you are targeting some of these camera systems which are operating at completely different focal lengths for depth perception.
Yeah. That's a great question. So different camera, they have different hardware systems. Like my research, although our threat vector, the attack surface are the cameras, but what we are really attacking are the models, the model itself. That's what we are really attacking. So I think for different camera systems, even if they are well designed, they would still have the vulnerabilities of taking those artifacts, right? So if you project lights, if you put fake images, they will still take it as real, right? And the model behind it will somehow they would perceive what it takes in. They don't understand what it is. They just try to do the object detector or depth estimation based on the data they have. Right, so it's in that sense it's agnostic for different types of cameras, right? If you have input data, if the model doesn't understand it, right, so you have the vulnerability, right? But definitely, I would say for different types of sensors, some cameras may have less this of artifacts, so they would be more robust against attacks, right? But the fundamental thing are the AI model itself; they are still vulnerable. Right, so there's definitely attack vectors that you can still compromise them.
Thank you.
Yeah.
So my second question is, I know Tesla has been pushing for like a camera-based solution for for building some of their models, but I think some other manufacturers are doing different things, like combining cameras with lidars or radars, stuff like that. So does combining some of these optical images with the signals that you get out of lidars or radars, do those combinations make some of these systems a little more robust?
More secure, more robust, yeah. I think that's true. That's true. So multiple sensors definitely can cover more cases, and also somehow it can detect attacks much easier. If you have single form factor like camera, right, and you can do all sorts of attacks and inject things into there, but the LiDAR and radar, they kind of provide additional data to prove that it's not real. So I'm a strong believer of sensor fusion. I think eventually Tesla have to add a radar. So that's what my personal view is. Basically, human can also make mistakes, right? So I say Elon Musk said that human can drive car perfectly, but it's not true, right? Human really make mistakes. So we need additional helps, right, from radar and other sensors to really perceive environment in better and in a more robust way. So in that sense, I think Elon Musk doesn't understand. Maybe I shouldn't put it here. Yeah. So security problems here. So I think it's really important to have multiple sensors.
Thank you. Thank you so much.
Yeah.
All right. Any other questions? Oh, okay, Dr. Yan, can I ask a quick questions? Now
Sure.
you just presented a couple of different types of attacks today.
Yeah.
But can you share, let's say, one very powerful or very simple, let's say, method to detect those attacks? For example, the last one, lens attack.
Yeah.
How we can detect it and how we can mitigate such attacks? Do you know any simple or powerful method
Yeah.
for that?
So one of the methods there's multiple methods. So the best approach, I will think, because this is targeting the depth estimation of the camera, and if you use multiple sensors like LiDAR as an input to the depth image, so you could definitely get a more robust depth information, and that's require you to add additional sensors, right? So it wouldn't be possible like with Tesla cars or other cars. And one simple approach is to do like scene understanding. So I think Tesla or some other car company, they are trying to do that, like try to make sense of the scene, right? Just like what I show in the picture, it's a high-level understanding. I think this deep learning, deep neural network foundational models, they can really now understand the scene well. So when you like are driving forward, you should have a consistent view of the object on the road. If somehow it changes radically, like at a certain time it changes, become bigger and become smaller, this violates physical law, right? So it should understand it and then give you a reasoning that something is wrong. And that could really help detect such attacks and prevent it even filter out like those kind of attack examples and to make it appear more natural. So this is a good way, like scene understanding. I think that's the next thing that we need to have in autonomous vehicle.
Good, thank you. I have another quick question.
Sure.
So when I'm driving, let's say if I'm driving in unknown environment, but let's say also when I'm more working on robotics, I know that GPS is also very popular sensor data.
Yes.
So can you give us some examples about what some common or maybe what common attacks on GPS sensor data?
So GPS sensor is vulnerable to signal injection attack, and basically you can like a fake. So some of my students have done this experiment. You can use a software-defined radio, USRP, to create a very like similar GPS signals to inject it to the GPS sensors. And the GPS sensors will regard this because it's more powerful, so it will take this as a real signals, right? So it will basically make a false judgment of the location. I think that's probably the most popular one. And you can also jam it. So jamming attack is kind of a pretty easy to do. You can, I even have a jammer like in my office. When I turn it on, like all the signals are blacked out, including 5G signals, Wi-Fi signals, GPS signals. Like all of them are wiped out. So jamming is pretty easy to do. Yeah.
Okay, all right. Maybe last questions. Yeah, just please use the microphone.
Thank you, Professor, for your presentation. I want. Do you think such perception issues can influence the decision-making step of autonomous vehicle?
Certainly. Yeah.
So, and how to address this problem?
So basically, like it's a different problem for traditional vehicles and the new end-to-end models. Like for traditional, so you have 3 stages. You have the observation, you have decision-making, you have the planner. So when you attack perception, it can impact the decision-making, right? So I can make enhancement to the perception to make it more robust, but I can also update my decision-making process, right? And this, like the most advanced way is using reinforcement learning to do this decision-making process, but they didn't think much about adversarial attack, although like some of the new research try to take this into consideration. But you can enhance the reinforcement learning to make this more robust, right? But there's another like a new approach is end-to-end AI model. In this case, you really need to deal with like AI models, right? So these are the methods that you can use to enhance AI models against those perception attacks and like decision-making attacks. So you just don't separate them. So it's all attacks towards AI models.
Okay.
Right. So you try to enhance AI models.
Thank you.
Yeah. So there are two different type of approach here.
Okay. Thank you.
Thank you for the question.
All right. Thank you, Dr. Yan, for sharing great work with us today. Let's give him a big round of applause.
Thank you, everyone. Thank you.
All right. Thank you for attending today's seminar. That's all we have today, and see you or next seminar. Thank you.